So here we would like to define some very basic things that we use routinely in a metric space. So let's start with convergence of sequences. So we will say, let's start, of course, it's better to first specify that we're in a metric space. So let x comma d be a metric space. And let's define a few things. So we will say that the sequence xn n in n of points of x. So the elements of the metric space can be referred to as points, converges to x in x if the distance between xn over x, this is a numerical sequence, tends to 0. Okay. Then we define an open ball in a metric space. So B of x comma rho is all the y's in x such that their distance from the point x is less than rho. This is called the open ball of radius rho centered at x. And of course, we have the closed ball. Now, we can find different notations in the literature. So here, oops, sorry about this. This is very wrong, what I wrote here. I meant d of xy is less than rho. So here, d of xy is less than or equal to rho. So this is called the closed ball. Of radius rho centered at x. And an open set in x is a set U with the property that along with any of its points, it has an open ball centered at any of its points. So is a set satisfying the following. If x is in U, there exists a rho greater than 0 so that the open ball centered at x with radius rho is a subset of U. So you have a little bit of space to move in all directions. Actually, the notion of direction is used here for illustration purposes. There's nothing like a direction in a general metric space. But pretty much this means that there is a way to move around any point, at least without formally leaving a set. And a set is closed if the complement is open. So that means that there is space to move around in the complement of that set. I remind you that the complement is the set of points that do not belong to our set. So if D, so D is closed, let's write it more formally. If and only if X minus D, which is the set of all points that do not belong to D, so X in X such that X does not belong to D, is open. There is a very nice characterization for closed sets. So this subset of X is closed if and only if for any sequence xn of elements of D that has a limit x that converges, its limit belongs to D. So in other words, closed sets do not allow their sequences to converge outside of them. Okay, and the reason is very simple. I want you to understand this in a very simple way. So imagine that you have a set D which is closed, and imagine that you have a sequence of points that belong to D, and somehow, magically, they converge outside of D. Here's why this is impossible, because if the limit is outside of D, then there is an open ball that surrounds the limit and is contained fully in the complement. Since the sequence converges to that point, because of the definition of convergence that says that the distance is 10 to 0, eventually that sequence should be in that open ball. Yeah, but that's impossible. That's too much to ask, because then you have points that first of all belong to D, and secondly belong to a ball which is completely outside D. Okay, so that shows you that every sequence that converges has to converge within D if we're talking about the complement of an open set. And we can also show that if this is the case, then the set has to be closed, because again, it's the same story here. It's a little more constructive. I could outline what the proof is. So if you have a set that admits a sequence that in which every sequence that converges and has elements in that set has to converge within the set, then the set has to be closed, which means the complement has to be open. Okay, because if the complement was not open, then you would be able to find a point so that no ball, no matter what the radius is, fully belongs to the set. By taking radii of those balls to become smaller and smaller and choosing points in those balls, you can construct a sequence that does not belong to your set and converges to the point. Okay, now it turns out that unions of open sets are open no matter how many of them you take. And intersections of closed sets are closed. Actually, the fact that these two statements are equivalent follows completely formally from a statement known as De Morgan's law that has to do with just set theoretic notion. So if you take the union of a bunch of open sets, so let me call the open sets U sub I, and then you take its complement, the complement, so this notation means complement, is the intersection of all the complements. So do you see now how this follows? Well, if you take a bunch of closed sets, all the closed sets are open complements of open sets. So if you take the intersection of those closed sets, then that intersection is the complement of the union of the complements, meaning of the open sets. So if you assume the first one, that unions of open sets are open, then this setting here is open, so its complement is closed. And it goes also the other way around, which means that you just need to establish one of them. And actually, the fact that unions of open sets is quite straightforward, because if you can move around a point, have a ball that allows you to move around in it in a set, certainly that will remain true if you pass to the union. Okay, however, so this can be arbitrarily large collections of open sets or closed sets, but not so much is true for the other way around. So if u comma v are open, then their intersection is open. And you can pretty much generalize this to any finite number of open sets. Same thing for closed sets. So if C comma D are closed, then their union is closed. And you can generalize this to finitely many closed sets, but not to arbitrarily many closed sets. Okay. So and now we can say what a discrete metric space is. So a metric space x comma d is called discrete if every one of its subsets, every subset, in other words, is open. So this is the best way of describing a discrete metric. That's why in a previous video, when I gave the example of a metric which I wanted to call discrete, I said that this is a discrete metric, or this should be considered as a discrete metric rather than the discrete metric. This is the best way to define a discrete metric space. And these are pretty much the basic notions that we wanted to give here. Thanks for watching.